For a system represented by this transfer function, where the numerator order of the polynomial is 2 and denominator polynomial order is 3, where m is less than n, for this kind of transfer function, how to find modal canonical form? So to do that, as m is less than n, we can directly find the partial fractions for this particular function. Before we do that, we need to find the roots of the denominator polynomial. So if we find the roots of the denominator polynomial, we can see s cube plus 9s square plus 23s plus 15 can be written as s plus 1 times s plus 3 times s plus 5. I was able to write it straightforward because I know the roots of this function. In your case, if you have a function, you need to find the roots to write it in this form. Then I can write this as a over s plus 1 plus b over s plus 3 plus c over s plus 5. Now we need to find the partial fraction coefficients value a, b, and c. So to find what's the value of a, we'll do limit s tends to minus 1, s plus 1 times the transfer function. So we have here the transfer function s squared plus 6s plus 8 divided by s plus 1 times s plus 3 times s plus 5. S plus 1 cancel, and if we substitute s equals to minus 1 value in this function and find the coefficient value, we will get 3 over 8. And similarly, if we find for b, limit s tends to minus 3, s plus 3 times the entire function that we have here. If we put this in this place, we'll get the coefficient to be 1 over 4. And similarly for c, if we write limit s tends to minus 5, s plus 5 times again the entire function that we have above, we'll get 3 over 8. Having known the coefficients a, b, and c, we can write the transfer function y of s over u of s again as 3 over 8 by s plus 1 plus 1 over 4 by s plus 3 plus 3 over 8 by s plus 5. Now output y of s can be simply 3 over 8 by s plus 1 times u, the input, plus 1 over 4 by s plus 3 times u, input, plus 3 over 8 by s plus 5 times the input. Now output is actually summation of first term, second term, and third term. We know if a transfer function is 1 over s plus a, this can be represented in block diagram as with a negative feedback with the integrator in the forward path 1 over s, and in the feedback path the gain is a. So we can represent it in this form. So now we know y of s is summation of all this, and all of them are in similar form as this, where a in first equation is 1, a in second is 3, a in third is 5. So now let us find the block diagram which represents this expression. For the first term, we can represent, if this is the input, we have a summation block with negative feedback. In the forward path, we have 1 over s, the integrator, and in the feedback path, we have 1 because the a value here is 1. Now this will be multiplied by a value of 3 over 8, and this will be the output, assuming this is u of s. So this is only for the first term that we have here. Now similarly, if we can write for the second term would be 1 over s at the output, because at this point of time we have here a is 3, so feedback path gain is 3, negative feedback, and the partial fraction coefficient here is 1 over 4. It gets multiplied with this. So this is the output of the second term. Of course, we have the input here. So again, u here. And the third term, we have 1 over s integrator, and output is fed back with a multiplication factor of 5. and with a negative feedback, and multiplication with 3 over 8, because that is our partial fraction coefficient, we get the output. Here is the input. Now our output y is actually summation of all these outputs. So we put a summation block where we add this value and this value as well. This will be output. So input we are supplying to all of the terms. So now this is how the block diagram looks, and if you are interested in signal flow graph, it is straightforward to convert block diagram to signal flow graphs. Now the question is, how do we represent them in terms of x dot is equal to a times x plus b times u, the state equation, and output equation c times x plus d times u, where x is a state vector, u is an input vector, and x dot is a differential vector, and y is the output vector. In this case, our system has only one output and one input, so y and u are single values. Now let us find x dot values here. If I take x to be x1 to be this, then integrator input would be x1 dot, and that is how we always choose. Output of the integrator we choose as one of the state variables. Now here we have another integrator, so this is another state variable x2, and here x2 dot, because x2 dot integrated will become x2. Now x3 here, so we have x3 dot. Now let us write the state equations for them. x1 dot would be equal to the input minus the feedback multiplication of x1, which will be u minus 1 times x1, u minus 1 times x1. If you write x2 dot, which will be u minus 3 times x2, and x3 dot would be u minus 5 times x3, and the final expression y is equal to 3 by 8 times x1, 3 by 8 times x1 plus 1 by 4 times x2 plus 3 by 8 times x3, and it doesn't depend on u directly, at least. So now let us write x1 dot, x2 dot, x3 dot. The differential vector, state vector, is given by the system matrix A, which is of 3 by 3, because the order of the transfer function is 3, x1, x2, x3, the state vector, plus the B matrix times u. Now x1 dot, it depends on x1 and u. It doesn't depend on x2 and x3. So x2, x3, 0. So x1 dot is equal to minus 1 times x1 and 1 times u. So we can write x1 dot as minus 1 times x1 plus 0 times x2 plus 0 times x3 plus 1 times u. So we can simply write this as this equation. Similarly, x2 dot is 0 times x1 minus 3 times x2, 0 times x3, 1 times u. Now x3 dot is equal to 0 times x1, 0 times x2 minus 5 times x3 plus 1 times u. So now we have completed the state equation. Now let us look at the output equation, which is y is equal to matrix C times the state vector x1, x2, x3 plus vector D times u. Now y depends on x1, x2, x3, all of them. So x1 it depends with 3 over 8, x2 1 over 4, x3 3 over 8, and it doesn't directly depend on input, so 0. This D vector can be 1 or some magnitude only when the numerator and denominator polynomial orders are same. We have seen this in previous video. This form is also called as diagonal form because we have all the diagonal values and rest of the values are 0. And especially these diagonal values are exactly the roots of the denominator polynomial, which means these are the poles of the transfer function.